Compute the diameter of the flow field in the far wake of a propeller of diameter 3.05 meters, which produces a thrust of 8.9 kilonewtons while flying at a speed of 322 kilometers an hour. Okay, so again, these are the equations we derived in a previous video, and in the question we're given some information. We're given the diameter, we're given the thrust, and we're giving the speed. So we have the diameter will allow us to get the area, we have the speed, we have the thrust, we don't have density, and I need to determine A. Okay, so we're going to have to make an assumption here, I think. So we're going to assume that the density is 1. Okay, it's 1 kilogram per meter squared. Right, so when we make that assumption, we need to convert the speed here. So the aircraft is flying at 322 kilometers per hour. I need to convert that to meters per second. So divide 322,000 by 3,600, because there's 60 seconds in a minute and 60 minutes in an hour. 60 by 60 is 3,600. So when I do that, I get the velocity is 89.4 meters per second. The area of the propeller disc is 7.3 meters, which is pi r squared. It's just pi r squared. This is my formula. So now I have 2. I'm assuming this is 1. I have my area, I have my velocity. I don't have the value for A. So A times 1 plus A is just A squared plus 1. We can rearrange the equation then. Plug in the values. So the thrust is 8,900. 2, we've assumed the density is 1. The area of the disc is 7.3, and the velocity is 89.4. So we're going to square that. When I do that, I get an expression, which is just a quadratic equation. Okay, so we're going to use the standard equation used to solve quadratic equations. And when I plug the values in, so the coefficient here is 1. So that's 1, that's 1. So that's my B, that's the A, and the A here, and this is C. So when I plug those values in, I'll get a value of A to be 0.071 or minus 0.1071. We always take the positive value because a negative value here would make no sense. Okay. So we take the positive value and we can calculate the efficiency, 0.93. We're not asked to do it, but why not? Okay, so we have efficiency of 0.93. What is important though is this value of 0.071. Okay, so I'm going to store that 0.071. And when we derived these equations, this is the image I used. And, we're just saying, when we derived it, when the air comes in, it comes in like this. And this is a bit like a Venturi, the air speeds up by a factor A. We call this the inflow factor, and that's this guy here. So the velocity at this point is the original speed plus this inflow or induced velocity AV, which can be expressed as V times 1 plus A. Okay, so we've just calculated A, so we'll be able to calculate the velocity here, which is called V0. So V0 is V times 1 plus A. which is 89.4, 1 plus 0.071, and that works out to be 95.8 meters per second. Okay, so I have the velocity, and we also know from some other videos that I did that from the continuity equation, the mass flow of air is equal to rho SV. So this is a general equation. So if I'm looking for the mass of air going through the propeller here, it's going to be rho S, but we're going to use the velocity here, which is actually going to be V naught. Okay, and I substitute in the values. So rho, we've assumed that to be 1. S was 7.3, we just calculated that, and we just calculated V naught to be 95.8. So that works out to be approximately, I think I rounded up here, right? It's rounded to 700 kilograms per second. So that's the mass flow of air going through the propeller. Now this is important because the mass flow going through here will also be the same mass of air going through there. And we're going to use this mass to calculate the area back here. We're going to call that area SS. Okay, the area at the slipstream. Right, so we have V naught is 95.6, and we have the mass at 700 kilograms per second. The velocity V naught, again from the video where we derived these equations, we said that this velocity here is the average of what's down the slipstream and what's in here. So the velocity here is the average of the velocity V here and the velocity Vs here. So to get the average values, you add them up, and if there's two of them, you divide by 2. Okay, I rearrange that equation to get a value for Vs. So then when we plug in the values, so V naught is 95.6, V is 89.4, we get Vs to be 102 meters per second. Okay, so the velocity here is 102 meters per second. We also know what the mass flow is here. So if m dot is equal to rho SV, if I have the velocity, we assume through all of this that it's incompressible flow, so the density will be the same. And if I have that, I can just rearrange that equation and get this value SS. So the mass flow is rho SV, so SS is the mass divided by rho times Vs. So the mass flow we calculated to be 700. We assumed this was to be 1, and we just calculated Vs to be 102 meters per second. From that, I get an area of 6.86. Okay, so the area is just a circle, so it's pi, the radius in the slipstream, pi r squared s. So divide 6.86 by pi and then get the square root of it, gives me the radius, which works out to be 1.47. And then double that to give me the diameter, and that works out to be, I think, approximately 2.95 meters. So that is the diameter of the flow field in the far. So the diameter here is 2.95 meters.